This is 13-2. So just a quick review here. We have polar coordinates written r comma theta, kind of reversed here. Theta is our angle, r is the radius. And so let's graph the polar point 4 comma 30, which you really start with this angle 30 degrees. So I pretend it's like this. I rotate it 30, and then I kind of shoot it out positively 1, 2, 3, 4. So there it is, 4 comma 30 degrees. Okay, now write another ordered pair for this point that would land in the exact same spot with r and theta both positive, r positive and theta negative, r negative and theta positive, and r and theta both negative. So pause the video and see if you can come up with those 4 points. Okay, so hopefully you did those 4. One positive way to do that, it would be 4 comma 390 degrees. All right, so in other words, we start here, we rotate 360, 390, and then go 4 again. R positive and theta negative, we could have 4 comma. Okay, phone call is done. Getting rid of this. So r positive and theta negative, so we could go 4 negative 330 degrees. That's 1. So in other words, I start like this, I go negative 330 degrees, I end up like this again, and I go out 4 positive. R negative, theta positive, so we could go negative 4, 210 degrees. So if I go like this and I rotate 210 facing this way and I go backwards 4, I would end up right there. And then finally both negative, I could do negative 4, negative 150 degrees. So I go like this, I rotate negative 150, again I'm facing this way and I go back, end up right there. Okay, next, just a little brief review, match the polar equation. We talked about this A and this B, one being larger than the other, how does that influence it, and just a few kind of other ones. So pause the video and see if you can match them up. All right, we're back. So if A and B are the same, that would mean it's just going to come together and not have a loop. So that would be F. That would be F. So like if cosine, think about some of the key points. At 0 degrees, this is going to be, cosine of 0 degrees, this is going to be a 1. So 2 plus 2 is going to give you 4. And then at 180 degrees, this is going to be negative 1. So you're going to get a 0 right there. Here, B is bigger, and when B is larger than A, again, that's going to kind of give you this little loop. So if we imagine at 0 degrees, this would be 1, so it would be 1 plus 2, that would give you 3 right there. Choice E, by the way. But at 180 degrees, when this is negative 1, we have 1 minus 2. So we rotated 180 degrees, we're going backwards. That's why we get negative 1 right there. Okay, when A is larger than B, we end up with this kind of bulging guy here, so it's going to be choice D. We again think about at 0 degrees, this would be 3 plus 2, so this would be 5. And then at 180 degrees, I rotate 180 degrees. This time, this is still negative, but this is strong enough or large enough to overcome that. It's still positive. 3 plus negative 2 gives me positive 1 here. Okay, and the rest of these, r equals 2 is our circle, that's B. R equals 2 theta, that's our spiral, that's A. 2 cosine theta, that is C. So that's our review. Let's go to the next page. Okay, polar and Cartesian coordinates. So, how do we connect these two ideas? So if I've got Cartesian coordinates x, y, so let's just go ahead and plot that, x, y. Let me turn on this lamp. That kind of helps. Okay, so if I've got x, y, let's think about how to represent that with polar coordinates. So I could have some kind of radius here, r, and then some kind of theta that, you know, I rotated first and then I went up to this r. And if this is x and y, I'm just going to label this x and y. Okay, so let's think about some relationships we could make here. So cosine of theta equals x over r. Multiply both sides by r, and we get a way to represent x is r cosine theta. Okay, sine of theta is y over r. So again, we could represent y as r sine theta. So these can be substituted for each other. Finally, if we just want to relate the sides, we can use the Pythagorean theorem. X squared plus y squared equals r squared. In other words, r equals the square root of x squared plus y squared. So these are some key substitutions that you're going to be making. So please be aware of those. Let's practice first by converting from polar to Cartesian. I'm just practicing here with radians just for fun, because we haven't done it as much. So 2 comma pi. Let's go ahead and just draw what that would look like. We don't have polar graph, but that's okay. So I'm going to rotate pi radians. So pi radians, that would be 180 degrees. Then I go out 2. So let's just go ahead and plot that. This is 2 comma pi. Again, this is r, this is theta. We call theta, we use theta even if it's radians by convention. Okay, you can probably guess the Cartesian coordinates, but let's use these little substitutions here. So again, x equals r cosine theta. Since theta is pi, I say, okay, our r is 2, cosine theta, so cosine pi, that's -1, so we get 2 times -1, or -2. Our y is r sine theta, again our radius is 2, and sine of pi, our height is 0 here, so we get 0. So our Cartesian coordinates, -2, comma 0. Okay. Why don't you try this one? So pause the video, see if you can do it, and then come back and unpause it, see if we get the same thing. Okay, back. Or maybe we never left. Let's take a look here at this polar coordinate, pi over 6. So I'm going to rotate pi over 6 like 30 degrees. I'm going to go out √3, so like that. That's r, that's theta. So that means this is my radius, √3, and this is pi over 6, or 30 degrees. Okay, so you can kind of draw the triangle if you want, if it helps you to think about it. X is going to be, again, r cosine theta. So our r is √3. Cosine theta, cosine pi over 6, cosine 30 degrees. We can kind of see this. It's the longer one. That's √3 over 2. √3 over 2, positive √3 over 2. Okay, so we get √3 times √3, that's √9, so 3 over 2 is our x coordinates. And our y coordinate is r sine theta. So in other words, √3 times sine at this pi over 6, sine pi over 6, or sine 30 degrees, the smaller one is 1/2. So we get √3 over 2. So our Cartesian coordinates at this point, 3 over 2, comma, √3 over 2. Okay, so that's converting. If we want to go backwards, let's go ahead and take a look at going backwards, going from Cartesian rectangular coordinates to polar coordinates. So again, I'm just going to sketch this. So we're converting this -1, 1 to polar coordinates. So again, let's think about this. So our r, this is our radius. We know that this is -1. We know that this is 1. And we need to find what this theta is as well, right? Because we need r and theta for our polar coordinates. Let's think about how we could get r. Well, r can just be made by just doing the Pythagorean theorem, because we have a little right triangle there. So r equals, and again, that's That's this little relationship right here, square root of x squared plus y squared, negative 1 squared plus 1 squared. So we get the square root of 2. Theta. How can we find theta? You can think back to earlier chapters. We just can we know that this is negative 1 over 1. Again, using our new school definitions, if we just look at the coordinate, we can take the arctan. We can take the arctan to find this. So if we go by definition, theta equals arctan of y over x, so 1 over negative 1, or arctan of negative 1. Okay, if you punch that in, though, it's going to give us, remember our principal branch for tangent is here. So it's actually going to give us this one here, negative pi over 4, or negative 45 degrees. So negative pi over 4 or negative 45 degrees if you prefer. So remember, we can always add 180 degrees to get something that also has the same tan ratio. So we'll say plus pi n, because we're doing it in radians. You could have also written, let me go down here, you could have also written negative 45 degrees. Stop being blurry. Come on. There we go. You could have also written negative 45 degrees plus 180 n, but we're using radians. So if I add 1 pi to that, 4 over 4 pi minus 1 over 4 pi gives us 3 pi over 4, which is 135 degrees. So if you did it like this, you get 135 degrees. So this is our r, this is our theta. So our polar coordinate is square root of 2, comma, 3 pi over 4. Right, that's r, that's theta. All right, try number 4 on your own. We'll come back and check it. All right, let's check it. 0, comma 2. So this one's a little bit different. For the r, again, I can just do square root of x squared plus y squared. And that is, my x is 0, my y is 2, and my radius is 2, which makes sense because I'm just going straight up. So you didn't really even have to do that. Theta, I can again try to take the arctan, to find this theta, arctan of y over x. Y is 2, x is 0, but that's going to error here because again we have an asymptote, we're dividing by 0 here, but we can look and just say by visual inspection, I'm just going to say by visual inspection, theta equals pi over 2, right? 90 degrees, pi over 2. So this is our r, this is our theta, our polar coordinates r, comma, theta. R, comma, theta. Okay. Just one more kind of cool connection to the graph that we already did. Like, let's say this was like 9. So if you remember, we did this exploration. This graph would be r equals, see if you remember, actually pause it and see if you can remember what this graph would be. All right, this would be r equals 9 cosine theta. A kind of cool way to see how that works, this is your r, and this is theta. You've got this triangle that you can form here. And if you remember from geometry, if the vertex is formed on the circle itself, it's called an inscribed angle. This angle right here, this is inscribed. And notice how this inscribed angle opens up to a semicircle, 180 degrees. If you remember from geometry, this inscribed angle is always going to be half the measure of this. So this is 180, this has to be 90. And so it's cool because even as we move it along here, it's always going to open up to this, so it's always going to be 90. So we can still use our trig ratios because we have a right triangle. So if we set that up, we know that this is r, this length is 9, right, from here to here. So I could just say cosine of theta, right, adjacent over hypotenuse, except my adjacent is this, equals r over 9, right? Adjacent over hypotenuse. If I solve for r, I get r equals 9 cosine theta. So it's kind of like a geometric way to confirm what we already knew about this graph using polar equations. All right, let's turn to the next page, excuse me. Here is a really funky one. I want us just to think. So what would this be? R equals, this is a really weird one. So just pause and see if maybe you can think about what this would be. Just think about it. Okay, let me give you a hint. If you're stuck here, let's say this is 6. So we have a specific case here, so this is 6. I can again make a trig ratio here, so cosine of theta equals, this time it's adjacent over hypotenuse. So this time it's my 6 over r. Let's see if you can figure out r. So if we solve, r equals 6 over cosine theta. In other words, 6 secant theta. So this is weird. It's just a straight line. It's really kind of interesting, but if you think about it, let's just pick a few of these. Like let's pick for theta, let's let theta equal 60 degrees. Let's do this one. Theta equals 60 degrees. So if theta equals 60 degrees, think about cosine of 60 degrees. Cosine of 60 degrees, so that's kind of like up here, right? That's going to be the smaller one, right? So it's going to be 1/2. So if I went secant, so secant of 60 degrees, it would be 1 over that, so 1 over 1/2, so it would be 2. Okay, so if I kind of plug that into my 6 secant theta, so 6 times 2, this would be 12. So at 60 degrees, so you can imagine this, when I tilt it to 60 degrees, you can kind of picture it being like, yeah, that would be kind of up there. Let's get really close to 90 degrees. You can see what I'm talking about. Let's do 89 degrees. So at 89 degrees, cosine of 89 degrees is 0.017. So that means secant of 89 degrees is 1 over 0.017, 57.299. And that's just for secant 89. If we want to actually plug it in here, 6 times that, I need to get my calculator. So 6 times 1 over cosine 89 degrees. So 343.8 approximately. So 89 is 343.8. So you can see that as we're getting close to 90 degrees, it's going super far up. It's going super far up. It makes sense it would still be on this line up here. And then if I rotate, let's think about like, I don't know, 120 degrees. So 120 degrees, I've rotated over like here. That means this must be, if I'm rotating here, it's actually kind of shooting out the back. It must be down here. It must be giving me some large negative number. Let's double check that. So at 120 degrees, cosine of 120 degrees, let's think about that. That would be negative, and that's going to be the smaller one, so that's negative 1/2, right? Just checking my work because this is a video, I don't want to make a mistake. So if I take the reciprocal, so secant of 120 degrees is going to be 1 over that, 2. So if I plug this in here 6 times that, it's going to give me negative 12. So yeah, that makes sense. So 120 degrees, I rotated over here, and then I just kind of went down here, so negative 12. So for this, it's a weird equation, 6 secant theta, no matter what degree we're at, it's always going to be forming along this line. And if I rotate past 90 degrees, I go here, it's forming starting down here. And you can plug it into Desmos and watch it. It's going to go up, and then it's going to start forming down here, and then finally get back up to here, and it's going to connect and make a straight line. So pretty cool. So based on that, try and fill in what you think these special circles and lines would be. Pause and come back. This is A, and A. your answers are r equals a cosine theta, r equals a sine theta, that's from before. We just talked about how this is r equals a secant theta. This is going to be r equals a cosecant theta. And if you're kind of confused about why that is, again, you can draw a triangle and kind of think about how that connects with secant, 1 over sine theta. You can also just kind of step through it on Desmos with a slider and see how it gets drawn and try to think about how that works. Okay. All right. We're right here. Let's turn to this page now. So we're now finally connecting everything to conics. And so if we could go back to the page, the Desmos exploration page, the URL is goo.gl/lowercase k, uppercase z, 62, uppercase I, uppercase A. And so I was going to have us graph these, but you don't have to do that. Basically just play around with the idea that if we take the reciprocal of our limicons, a plus b cosine or a plus b sine, so on and so forth, if we take the reciprocal of them, we will make conic sections. Excuse me. And so actually, why don't we use the other page first to explore a little bit, and then we'll come back to this page. So we flip over to this side. Excuse me. Here are 3 different limicons, one with the loop, one with no loop, and one with the kind of bulge. And they're oriented around this y-axis, kind of pointing upwards. So it's going to be sine, it's going to be plus. See if you can recreate these on Desmos. And then just take the reciprocal. So just type 1 over and see which one goes to which. So just go ahead and pause the video. Go ahead and type these into Desmos and see if you can figure out which one goes with which. Okay, so hopefully you've explored a little bit. And so for our limicons, first let's just kind of review this. For this one right here, if there's no loop, remember, that's going to be the case where a equals b, or sorry, yes, a equals b, absolute value of a equals b. So that's r, this is r equals 3 plus 3 sine theta. Again, we think about what happens at our key points. So in this case, it's 90 degrees, because at 90 degrees, sine is 1. So if you think about that, 90 degrees sine is 1, so we have 3 plus 3, that's why this is 6 up here. At 270 degrees, so I rotate over here, 270 degrees, sine is -1. So 3 plus -3 would give us 0 at 270 degrees. Okay, for this one with the loop, that's the case again where b kind of overpowers a. And so that's the case where b is greater than a. So this is going to be 2 plus 3 sine theta. And again, we examine what happens at our key points. For sine, it's 90 degrees and 270. So at 90, this is 1. So 2 plus 3 gives us 5. That's why this is at 5. But at 270 degrees, sine is -1. So we think about, all right, 2 minus 3 is -1. So what happened is we rotate. We're facing this way, but we go backwards this way, so we end up right here. And then finally, if there's this bulging outward, that's the case where b cannot overpower a. A is strong enough to withstand b even when it's negative. A is greater than b. So something like this. Because again, examining at 90 degrees, we get 3 plus 2, still 5. But at 270 degrees, so I rotate over, I forget which way is the positive, we'll just say it this way, 270 degrees, so that's -3 minus 2 is 1. That's still positive though. Remember, we're facing downward, so this is actually going, this is +1, so we'll end up right here. Okay, so for the reciprocals, if you just go to Desmos, type 1 over each one of these, we're going to get the fact that this one goes to this one. This is a parabola, 1 over 3 plus 3 sine theta. Oops. Excuse me. This one is a hyperbola, so this is 1 over 2 plus 3 sine theta. And this is our ellipse, 1 over 3 plus 2 sine theta. All right, so let's go ahead and kind of combine this with our rules. So if the limison at the very top has a loop, if the limison has a loop like this one, it's going to be a hyperbola. And that's the case where, again, B is stronger than A. So if the limison has a loop, then the conic is a hyperbola. Again, that's the case where A gets overpowered by B. If the limison has no loop, like this, then it's going to be a parabola. Oh, sorry, if it has no loop, let's see what am I doing here. Then it's going to be an ellipse. Sorry, this is the no loop one. This is the cardioid, excuse me. I've been mixing this up. No loop, that's going to be the ellipse. An ellipse. Okay, so for the ellipse, again, that's the case. No loop, that's the case where A is strong enough to withstand B, so A is greater than B here. And finally, if it's a cardioid, that's like the heart-like shape, then it's going to be a parabola. Right, and the cardioid is when they're exactly the same, so at like 270 degrees for sine or 180 degrees for cosine, they cancel each other out, and we get that, so the 0. Okay, so reciprocal, here it is. Let's go back to the previous page. Just briefly flesh this out a little bit more. So this is our general form of a conic section with one focus at the pole. Again, the pole is the origin. All right, so just a few more things. The eccentricity. The eccentricity of the conic, we barely talked about this. Let me write it first. Is going to be the absolute value of B over A. B over A. Hold on one second. Okay, and you can fill this in. I'm absolutely not going to ask you this, but to find this K number, I mean, we've just been using 1, but absolute value of K is equal to the absolute value of A times the eccentricity times P, where P is the distance between the focus and the directrix, which we have not talked about at all. So don't worry about this. But eccentricity, just conceptually, we briefly touched upon it. So eccentricity, again, is like, eccentricity is kind of like how out of round something is. How out of round something is. So if you remember, for a circle, a circle is not out of round at all. So our eccentricity is going to be 0. An ellipse is kind of out of round. A hyperbola is more out of round. So let's just kind of review what we talked about before. I'm just going to go to these web pages we did. Excuse me. So if we have an ellipse, it'd be kind of like that. A parabola is going to have an eccentricity of 1. Hyperbola, anything above 1. And if I flatten it out all the way, our eccentricity is going to be infinity. So we have something like this. Our hyperbola, I'm just going to kind of mess around with this. Our eccentricity is here. As I move this around, though, you can never get it to be less than or even equal to 1. It's just going to be kind of, oops, you know, even if you make it straight, it's 5, pretty big, right? 16, oh, infinite. There you go, I made it straight line. But you can never make it less than 1. For an ellipse, oh, there it was again. Again, the same thing. If I make it a circle, my eccentricity is 0. It's not out of round at all. If I try to make it more out of round, again, I can increase it. You know, it's increasing. It's more and more out of round. But no matter what, it's going to just top out at 1. So I can't get it above 1. All right. So again, our rules, oops, are like this. So there it is. Eccentricity parabola is 1, 2, and then infinity. Okay, so again, our rules, if B is less than A, this is kind of stated backwards. So if A is stronger than B, it's able to withstand it. That's going to be an ellipse. It's an ellipse. And again, for an ellipse, our eccentricity is going to be something less than 1. If B is overpowering A, it's going to have that loop again, and that's going to be a hyperbola. Our eccentricity is greater than 1. And finally, if they're equal, like in the case of our cardioid, it's going to be a parabola. Eccentricity equal to 1. So let's kind of test this out. B is less than A, B is greater than A, B is equal to A with these different eccentricities. Let's go back to Desmos. So if we go to our exploration here, if you haven't, I'm just going to copy this, push enter, and push paste. And then I'm going to just do 1 over, you could just retype A plus B sine theta. Oh, that looks kind of funky. That's pretty cool. So now I've got these two reciprocal functions. These are both blue. That's kind of annoying. So what you can do is click Edit, click here, and change the color red. Done. So we see here, again, when I have this cardioid, the eccentricity is 1 right now. Why? Because A and B, they're exact same, right? If A and B are the same, no matter what, it's going to be a parabola. It's going to be a parabola. I can switch this to be cosine. Cosine, and this would be cosine. And look, it's still a parabola. If A is equal to B, it's going to be a parabola. Okay, now let's take a look if A is less than B. So A is less than B, so B overpowers A. Again, that's when we have this loop here. And our reciprocal function, the red one, is going to be a hyperbola. You can just mess around with that. And then finally, when A is greater than B, that's where we have that kind of bulge. So something like that. So we have this bulge. Our reciprocal function is an ellipse. So there we see it. So you can kind of see that. Finally, since eccentricity is the absolute value of B over A, to get the eccentricity to be 0, this has to be 0. And if that is true, we look in here, we have finally created our circle. Finally created our circle if you move B to 0. All right, so that's our conic sections. You don't have to graph these if you don't want to. So let's try to remember these connections here. I'm just going to rewrite the eccentricities here. Maybe you can pause the video for a second and see if you can remember what the eccentricities are for hyperbola, ellipse, and parabola. Okay, again, if it has a loop, then it's a hyperbola, right, this reciprocal function. So hyperbola eccentricity is greater than 1. If it has no loop, then it's an ellipse, that's the bulge. So it's A is greater than B, it's able to withstand it, so the eccentricity is less than 1. Finally, if it's a cardioid, A is equal to B, the reciprocal function is a parabola, and the eccentricity is equal to 1. All right, let's move on to the last page. So let's apply this. Okay, so let's think about what we have here. Show algebraically that this equation, r equals 9 over 5 minus 4 cosine theta, is an ellipse by transforming it to Cartesian form. What is one focus? We're not going to talk about a focus. What is the eccentricity? Why don't we just do that right now? So remember, this is our A and this is our B. Here, A is stronger. A is greater than B. So if we were to graph not the reciprocal, but just this, we would have that bulge with no loop because A was able to withstand B. But this is the reciprocal. So let's find our eccentricity. And remember, that's B over A. B over A, absolute value. So negative 4 over 5. So that's going to be 0.8. All right, and that fits because remember, eccentricity is less than 1. That's going to be an ellipse, right? That's going to be an ellipse, which it is. It's pictured right here. So now let's talk about how we can convert it to Cartesian form. The key is to picture again our relationship between polar coordinates and Cartesian coordinates like we talked about. So always just redraw this if you get stuck. So you have this x comma y Cartesian coordinate. I'm going to draw my radius r, draw my theta. So I've got x, this is y. So remember our relationships here. So cosine of theta equals adjacent over hypotenuse. So if I rewrite that, x equals r cosine theta. You can work that out if you want. It's basically cosine theta equals x over r, multiply both sides by r. You can also go back to the earlier part of the video, y equals r sine theta. And then finally the Pythagorean theorem, a squared plus b squared equals c squared, x squared plus y squared equals r squared. So r equals the square root of x squared plus y squared. We did all this earlier on, so I'm not going to spend too much time on it. But this is the three facts we're going to be using here. So let's go ahead and convert this to Cartesian form. So r equals 9 over 5 minus 4 cosine theta. I'm going to multiply both sides by 5 minus 4 cosine theta. I'm going to distribute the r, so we get 5r minus 4r cosine theta equals 9. Okay, so what we see here is that we have got exactly the type of things that we were looking to substitute for before. We got our r here, and then we've got r cosine theta right here. So I'm going to plug in x, and I'm going to plug in square root of x squared plus y squared. So right here I'm going to write 5 times square root of x squared plus y squared minus 4 times x equals 9. And now I've gotten rid of the r's, I've got rid of the thetas. This is all just Cartesian coordinates. It's kind of messy though. I've got this square root here, I've got the regular x hanging out here. We got to get rid of this square root before we can really work on transforming it. So let's move this over. 5 times the square root of x squared plus y squared equals 9 plus 4x. So that's a little bit better. Now we can get rid of the square root by squaring both sides. Let's square both sides. In fact, just so I don't make a mistake, I'm just going to write it out twice. So I'm going to square this. So this squared, 5 times 5 is 25. This squared is just going to give me x squared plus y squared. And that's going to be 9 times 9, 81. Let's see, that's 36x. That's another 36x. 36 plus 36, 72x. And this is 16x squared. Much better. So no square roots. Now we've just kind of got our classic turn this into a ellipse that we practiced. This is kind of like not general form, it's almost general form. Let me just distribute the 25. Now this is getting closer. Again, for general form, we want everything to be on one side. So why don't we leave the 81, because again we want to keep this number here, and move these guys over. So let's subtract 16x squared from both sides. And we'll subtract 72x from both sides. And I'm going to come up here where I have room. So I had 25x squared minus 16x squared. So 25x squared minus 16x squared is going to give me 9x squared. And then I've got my negative 72x. Let's see, I got plus 25y squared equals 81. So finally this kind of looks like our general form if the 81 was over here. So again, we want to complete the square. I factor out a 9. X squared, let's see, 9 times what gives me 72. That's 8. Since there's a negative, I'm going to go like this. I'm going to put a space right here. Don't have to do anything with the y. It's already a perfect square. All right, so again, to complete the square, we take this term right here, we half it and square it. We take this number, we divide it by 2, and we square it. So negative 8 divided by 2, that's negative 4 squared, that's 16. So we're going to add 16 to both sides. Except really, I shouldn't say that, I didn't add 16, I added 9 times 16. 9 times 16 is 144. So I'm actually going to add 144. Right, 9 times 16 is 144. So I'm going to add 144 to both sides. Okay, so now after completing the square, I've got this. This is a perfect square trinomial. I've got 9 times x. Let's see, x plus 4 times x plus 4. Nope, this is a minus. So it's x minus 4 times x minus 4. So it's x minus 4 squared plus 25y squared equals, I just look at this, and that's 225. Almost done. Divide everything by 225, because we want a 1 over here for standard form. And let's see, 25 goes in here 9 times, right? 25 goes into 225 9 times, so I can make this a 1 and this is a 9. 9 goes in 25 times. So this becomes a 1, this becomes a 25, and our final form here, x minus 4 squared over 25 plus y squared over 9 equals 1. So what we see here is our center. Our center is at 4, 0. We look for the bigger number. It's an ellipse. A equals 5. A equals 5. B equals 3. So we're going to go 4, 0. 1, 2, 3, 4. Yep, that looks right. I'm going to go 5 in the x direction. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'm going to go 3 in the y direction. And yep, that is it. So why don't you try, I'll leave this up here, why don't you try number 2, pause and try number 2. The graph is wrong, sorry, this should be not 0.5, this should be 5, 10, 15, negative 5, negative 10. If you're doing it Cartesian style, if you have it polar style, you can leave these positive, but definitely multiply everything by 10 here, sorry about that. So if you're doing Cartesian, you can label it negative 5, negative 10. If you're leaving it polar, you can leave these positive, but please multiply everything by 10. Try this one, and then we'll finish up by playing this and checking it out. Okay, so let's take a look here. Let's plot the graph afterwards, actually. Let's show algebraically. Let's find the eccentricity. So eccentricity again is the absolute value of b over a. So in this case, b is stronger. So if we were graphing the normal one, we would have a loop. So the reciprocal is going to be a hyperbola. Let's check it out. So we have negative 5 over 3. So that would be 1 2/3. So it's definitely above 1. Right? Our eccentricity is greater than 1, which means it is going to be a hyperbola. It is going to be a hyperbola. Okay, let's do the algebraic part first, and then we'll sketch it at the end. So r equals 16 over 3 minus 5 cosine theta. So again, we want to multiply both sides by 3 minus 5 cosine theta. So we have, I'm just going to kind of do a little bit faster, minus 5r cosine theta equals 16. We use our same rules. So for r, I'm going to plug in square root of x squared plus y squared. For r cosine theta, I'm going to plug in x. And then we will have gotten rid of our polar form, and we'll be kind of closer to our Cartesian. We'll be in Cartesian coordinates. We'll just have to kind of clean things up. So square root of x squared plus y squared. This is 5. Oops, mouse, get out of the way. 5x, and this is 16. So again, this is a little bit, we're going to square this, so let's move this over here. So 3 times the square root of x squared plus y squared equals 16 plus 5x. I'm going to square both sides. I like to write it out so I don't make a mistake like I did when I was practicing this. That's 9. Okay, so that's 9 times, this whole thing is going to just lose its square root when I square it, so I'm just going to do that, 9x squared plus 9y squared. 16 times 16 is 256, Mr. Blurry. So 256, come on. 256, and then 16 times 5 is going to give us 80. and then 16 times 5x is going to be 80x. So 80x, 80x, so 256, that's this one. This is 80x and 80x again, so it's 160x. And then 5x times 5x is 25x squared. Okay, so again, let's get everything on one side. I've got, this is the bigger x squared, so let's move everything over here this time. So I'm going to subtract 9x squared and 9y squared, leaving 0 over here. I have no y squared, so for right now I've got 0 equals 256. Let's put the x squared first. So 25x squared minus 9x squared is 16x squared. Oh, I've got 160x, and I've got minus 9y squared. This is like our general form now. Let's kick this guy over here. So we have negative 256 equals this. We've got this linear term here, so let's complete the square. 16 times x squared plus 16 times what? That's 10x. And then we're going to leave a blank to complete the square. And this doesn't need anything. So again, we want to complete the square. We want to take this number, this b term, this linear term, and I want to half it and square it. Half it and square it, so that 10 over 2 is 5. 5 squared is 25. That's what you add. If that's really random sounding to you, again, the basic 1-minute explanation for that is, if we just look at this trinomial, x squared plus 10x, and I go and like draw like algebra tiles, and this is our x squared, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 x's. All right. That's clearly not a square, right? It's like a rectangle. But if I take half, 1, 2, 3, 4, 5, I take these 5 bars and move them down here. 1, 2, 3, 4, 5. So I cross these guys out, and I arrange them like this. 1, 2, 3, 4, 5. Now this kind of looks like a square, right? But I have to fill in these little dots with little algebra tiles. How many do I have to fill in? Well, 5 times 5. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And now this is a perfect square. So in other words, I had to half the 10x to be 5x, and then square it to get 25, and now this is a perfect square trinomial. If I want to break it down into factors, I've got, just this is not x squared, this is x plus 5, and this is x plus 5. So we get x plus 5 times x plus 5 is x plus 5 squared. And so that's kind of the 1-minute explanation. So 16 times, factor this, this is x plus 5 squared minus 9y squared. And I totally forgot, just like I warned you not to do, to add this to both sides, right? I didn't add 25. I actually added 16 times 25. 16 times 25, let's see, that's 250, and 6 times 25 is 150. 250 times 1 plus 150 is 400. So this is not negative 256. It's 400 minus 256. So 400 minus 256 is 144. All right, so we can divide everything by 144. So that becomes a 1. So we can be in standard form here. 1 equals 16 goes into 144 9 times. This becomes a 1. This becomes a 9. 9 goes into 144 16 times. And so in the end, we are going to get ourselves, because this minus a hyperbola, just like predicted. Eccentricity greater than 1. Our center is at negative 5, 0. Our a is not the bigger number. Our a is 3. Our b is 4. Our a is the positive number. Square root that. A equals 3, b equals 4. So if I'm going to graph that, I go right here, negative 5, 0. I'm going to go out 3 in the x direction. Sorry, this is a bad graph. 3 this way, 3 that way. I'm going to go 4 up, 4 down, so kind of like almost up to here, almost down to here. I'm going to draw my central box. I'm going to draw my asymptotes. Okay, Okay, and then I look to see which is the transverse axis. It's the positive one, not the bigger one. It's X, so it's going to open up in this direction here like this. All right, and what you can do is you can go to Desmos, type in this first, polar coordinate. It should look like that. Type in this. They should be exactly the same. It should land right on top of each other, just like this. So that is the end of our lecture.